So Introduction to Physics, Unit 0, Chapter 0, Introduction to Physics. We're going to go over a lot of the concepts that every science class does in this first unit. Some of them at the end are going to be more specific to physics, because we're not going to look at chemistry and matter as much. We're going to worry about, well, what measurements do we need to worry about with physics? There is crossover in that we need to know our measurements, we need to know accuracy and precision, significant figures, and converting. But in physics, converting is so that you get the right labels in the right place so that you can use the equations properly. And so that you can even label things properly. In chemistry, converting was to set you up for stoichiometry, because that's what that was. Here, converting becomes a part, and then it allows us to then potentially use the equations that we need. At the end of this unit, we will have added vectors, which is, for some, maybe the first time you'll see it. I want just to make sure that and some of you have seen, oh, sine, cosine, tangent, I got that. Law of sine, law of cosine, I got that. However, we want to make sure that everybody sees the same thing. And kind of here's how I say it, and this is where it will be, and this is where I love physics, is that there's sometimes more than one way to get to the same answer. And seeing all those different variations can be fun. So, what is the fundamental goal of physics? It is to discover and understand the laws that we are observed in that phenomena. It's a branch of knowledge that involves the study of the physical world. That's why physics. Thank you, Sheldon, that said physica. Just like all areas, we do rely on that scientific method. It is always there. Kinematics is the first part that we do, and that's describing the motion. Dynamics says, why is it moving? And we can all look at a car rolling down the street, and you're like, and if there's nobody in that car, you're like, oh, look, it's moving. That's kinematics. The next question is, there's nobody driving. How is it moving? That's dynamics. Maybe it was a failed TikTok. I don't know. Scientific method hasn't changed. You observe, you hypothesize, you experiment, you analyze, you conclude. These are things that we look at in our labs fairly frequently. We observe what is being done. We make some measurements, so to speak. Some of our labs, we really focus on some of these parts where it becomes the focus is I give you the experiment, you then just analyze and conclude. The later labs, usually at the end of a unit, after you've experienced how to kind of make some of these measurements, I'll give you a problem. You then have to hypothesize how to solve that problem, develop your experiment, and analyze and conclude. Makes life a little bit more difficult. However, that's why they're summative. And you have to kind of really pay attention to, like, how am I going to do this? What is the problem? And it's very open-ended, and that's the frustrating thing sometimes. But that's science. It's an open-ended question. So you have to use the scientific method. But you have to have that scientific method. Very rarely do you ever get to a theory, and a theory and a law are two different things. Theories explain. Laws are a definition. Theories are like, you maybe would look at it, the theory is like the Constitution. It's kind of ever changing, okay? And how you interpret some things. The law can be changed, but it takes a much longer process. You know, the law of conservation of matter cannot be created or destroyed, is as simple as that. In the early 1900s, we had to say, in a non-nuclear process. Because a nuclear process, as we know, E equals mc squared, a theory forced us to change a fundamental law. Actually, two. Because then we also have the fundamental law of conservation of energy. Energy cannot be created or destroyed. It just changes its form. Gets to be the added part of it. And that energy can be created into mass or matter. That is a different form of energy. That's the potential energy. So these are, everybody would love to have, I want to have the Peterson theory or the Peterson theorem. You don't even have a Peterson hypothesis. Okay? Maybe that's the thing for physics will be somebody will invent and find the Peterson theory, and you have to name your first theory after me. Chances are it won't work that way because it takes many years. Big leaps. It takes, we have a lot of understanding about Einstein's theories. We even have experimental evidence to prove his theories true, but they're not laws because we still don't have a defining point to it. It still isn't an explanation of why we're seeing what we're seeing. So it's that explanation, theory, law, very defined. Variables are the things that we would love to control as much as we can. However, we can't always control them. That's also a big problem with the current affairs is we want to control all the variables. We want to control everything. I'm a control freak. I like control as much as I possibly can, but then all of a sudden there does become a variability of human nature. And you can't control that. We can control temperature, pressure, the amounts of matter we use, such as in mass or volumes. We can control what objects we're using. So we can control some of the variables, but we can't control all of them. And in this class, if we try to take into account some variables that might be small, and they might have a small effect on our results in the lab, we start to engineer it up a little bit. We start looking at too much of the little stuff. Some of them we have to just take it as that. It's a small variable. It might have small amounts on our results, but what's the big picture? So controlling variables isn't always easy. Doing what we can to finish off is very important. Our measurements. This becomes a little bit also of a thing. We have base units, Those are things we can directly measure, such as length, time, mass, electric current. We don't get to that in this class. Temperature, the amount of substance, which for some of the students that have taken chemistry, that word might bring up some very strong emotions. And then the one that I always love, luminous intensity, and the name they call it, candela. How bright something is. Candela. It's like, oh, a candle. That's one of my favorite ones. Now these are also the SI base units. Do we make all measurements of mass in kilograms? No, we don't deal with just kilograms, but our equations want us to. We in the laboratory will do a lot with grams because it's smaller. We then have to convert it to kilograms. Now derived units are taking these measurements and using an equation of some sort to determine another equation or another unit. The simplest way would be, say, that velocity is equal to distance divided by time. You'll get this equation again. Distance or length, base unit. Time, base unit. Velocity, derived unit. Velocity is usually reported in meters per second. You drive your car, the speed limit is a derived unit. How far you go over a time in miles per hour. Derived unit. When you see that per, usually a derived unit. Another derived unit that we commonly use is the Newton. That is a derived unit of a derived unit. See, it's actually mass and acceleration. Acceleration is a derived unit. It's velocity, how fast something goes with velocity. And then converting. Something fairly simple. We tend to use it a lot in this unit. We will stick around those three as our main converting points. That doesn't mean in your homework that you are still gonna not have to worry about anything bigger, smaller, than what we have. It might even be bigger than giga. It might be tetra. Okay? And that becomes the, well, where are you getting those numbers? Same place most people get numbers. Google. Okay? So some of these ones that are much bigger and much smaller are just that. It's all based on 10. Okay? That's the easy stuff. And that kind of gives you some reminding, hopefully some ideas of what your homework should look like.